Hi there everyone, how are you doing? In this video, I'm just going to do a quick demonstration of using SolidWorks to do a finite element analysis. And in doing so, I'm just going to make use of the tutorial problem that we're going to be looking at in class this week. So let me share my screen and we'll get started. All right, so here's the problem. It's just taken from the recommended / required textbook, the MOT machine elements in mechanical design. And if you have the e-text version, then it's on page 200. So it's design example 5.4. So we're going to go through this in class and make use of this to revise some of the solid mechanics stress analysis, deflection analysis that you should have done back in previous subjects such as mechanics of solids or applied mechanics and design A and so on. So yeah, so this is what we're going to look at. As you can see, it's in SI units, so we're going to use SI units to start with anyway in SolidWorks. And we're just going to build this model. So hopefully most of you are fairly proficient in SolidWorks by now, but I'll just do a quick recap and actually create the model and go from there. All right, so just as a caveat on what I'm going to show you, this is not a how to do FEA. There's whole textbooks on that. And in fact, if you go to this page where you'll find this video eventually, you've got the link to this textbook here. I call it a textbook, but it's not really. It's a very easy to read guide on how to do finite element analysis for design engineers. So there's not heaps and heaps of matrix equations and so on. It's a very easy to read book. And, as I said here, there's warnings and tips and guidelines in here that I see most students ignoring. And I see students making errors in their capstone projects that render essentially what they've done useless. And that those errors are clearly warned about in this book. Right, so this is not a subject for how to do FEA, but I'm going to make use of it to show you how you can make use of FEA to help you with your designs and with your understanding of solid mechanics. Anyway, so let's get on with it. Here's the problem. Just a rod here with a rectangular cross-section bar. I'm not going to bother to model the support here, as the textbook's authors also didn't do that. They've just used constraints or fixtures that we'll talk about. All right, so let's model the shape. So let's move that over there so we can see it while we're modeling. All right, that'll do. All right, so we'll start a new file. Start a new part. Okay. And make sure we're in features, and we're just going to create an extruded boss base. So I'm just going to choose the front plane. Now, one of the things that you'll note here is that the coordinate system in SolidWorks is different to the coordinate system in the textbook example. So you can see here Z axis is upwards, X is along the axis of the rod, and the Y axis is along the longitudinal axis of this rectangular bit here. We're going to build the model in the same orientation that it's shown in the picture. So we're going to have differences in our coordinate systems, and that's not an unusual occurrence. So you need to be able to deal with that. So I'm going to start with the front plane. I'm going to sketch my circular profile. What I'm going to let me just put that in here. What you can see is that it's not in imperial units or US customary units. So I'm going to change that for now to that, and it throws me out of sketch environment. So I need to go back in there to change that sketch. So if I go back, right mouse click, edit the sketch, and I now want to dimension that sketch in inches. So it's 1.87857 there. If we scroll down over here, I think they find out that they have a, scroll down a bit further. I think they set it at 1.1. Yeah, so they come up with 1.05. So they say, let's make it 1.1 inch. So we're going to do that, 1.1 inches. That's our diameter. And we can exit out of here. Now we've just got a sketch to make our extruded boss base. We need to, I could have pre-selected that, would have made it quicker, but let's go in here, select the sketch. And now I need to extrude that along. So if you're doing this for the first time, the default will be a blind extent or direction. So that's what we want for this. So let's have a look over here. What was our size for that? I think it's 8 inches. Let's scroll back up to our, yeah, so 8 inches. So let's put that in. 8 inches. Hit the screen. So there's the circular rod, part of this structural component. And next we want to model the rectangular bar. So again, let's do an extruded boss base. And as you should be aware, there's many options for how to do this. I'm going to choose the front, or this front face here of this part, or this feature that we've just created. And I'm going to sketch, let's zoom out a little bit, sketch a 2-point rectangle. All right, so now we need to constrain this. So I'm going to choose a center line, and I'm going to go from the center of the circle to the midpoint. There it is. So the pencil's covering in the eraser end of the pencil's covering over the little icon there. But yeah, just make sure when after you've clicked that you've got the midpoint constraint, not the just constrained to be on a line. So if we exit out of that and click on that and make it horizontal, so that will constrain our rectangular bar to be where we want it with respect to the circular rod here. All right, so now let's have a look at the dimensions of this bar. So we've got from the height, we can click on here, and that is, oh, so that's part of their design. So in the example problem in the textbook, it does it as a design problem. So it works out what do these dimensions need to be. We're going to look at it just as an analysis problem and choose some dimensions to start with. So again, I'm just going to skip down here and see what they came up with for those dimensions. So that height was 1.25 inches. So I'm going to put that in, 25. So that constrains our height. Now we need to put in the length. And if we go back up here, our length was 12 inches, but it's not the full length of the rectangular bar. It's to the center of this circular rod that we need to be 12 inches. So let's put in another center line or construction line is how I prefer to think of it. So I'm just going to put a vertical construction line somewhere here and escape from that. And I'm going to select the center of the circle and that construction line that I've just made, and I'm going to make it a midpoint constraint. All right, so now if we grab on a blue thing and try and move it, we can see what's still free. All right, so we can now smart dimension from the center of the circular rod to the end of the bar, and that needs to be 12 inches. And we can choose any length we like here because it's not given. They haven't told us what it is. So let's grab that and that, and let's make it, I don't know, 1 inch will do. All right. So let's exit out of there. Let's go to our trimetric view. So now we've got a choice of extent for this rectangular cross section, or this rectangular bar. It's, if we look back, go back down, you'll see that it's 0.375. I'm not going to scroll down for the sake of brevity. Right, so it's that. Now, I'm pretty sure that when the authors modeled their part, they just did this. But if you do that, you'll get the bending load on the this cylindrical part wrong. Right, so what I'm going to do is, instead of blind, I'm going to make it a midplane. Right, so the midplane of this rectangular bar is coincident with the end of the circular rod. All right, so let's click on that. All right, and there's our model done. Okay, we could model this back plate if we wanted to. I'm not going to worry about it for this quick demo. So now we've got our structural shape modeled. We can now go in and do a finite element analysis, or a simulation as it's called in SolidWorks. So click on simulation, new study, click on new study. And in my case here, I've only got static as an option. And really, whenever you're doing any simulation, you should really always start with just a basic static study to understand what's going on before you're trying to do anything more advanced down here. All right, you can give it another name if you want. I'm just going to leave it static 1 for now. All right, so there's our part. At the moment, we've just got shape, just got geometry. It doesn't know what material it is. Okay, so you can see here material not specified in the SolidWorks modeling part of it, and it's also not specified here in the simulation part. So I'm just going to specify it in the simulation in the FEA. So apply, edit material, click on there, and you can try and scroll through here to find out what material. So in the tutorial problem, or the example problem in the textbook, they've used SAE or AISI 1340. Now that's not here in the standard list of SolidWorks materials. You can click them through and see if you can find the one you want. So let's just put that to imperial units. So it's in PSI to match what we've got over here. So here, right, we've got given the yield strength and ultimate tensile strength. We're not given in this part of the problem the Young's modulus and other details. You need to look up Appendix 3 for that. Okay. All right, so yeah, so you can try and find the closest one, or you can look up how to create a custom material, which is what I've done here. So I'm not going to go through how to do this. There's plenty of information on, if you click on the help in SolidWorks, so up here, that'll tell you. There's many tutorials that show you how to do that. So I'm going to select the one that I created before, the AISI 1340. And then I've just put in SI units. And you can see I've got the values here. So 102 KSI and 63 for KSI for yield. Yep. And I've had to look up these other values in Appendix. So let's apply that. And close. And we can see now here that got a green tick here, and we've got material applied. So we don't have any connections. These are for connections, welds or bolts or things like that. What we do have, though, is to model this connection at this right-hand end here of the circular rod to this backplate or this rigid surface. So we're modeling that as a rigid surface. So that's a fixture, right mouse click, and we're going to be really simple and, in fact, wrong, really, but don't worry too much about that for now. This is just how to click on the right buttons to get some colors that show you some stresses for now. All right, so we need to set that, and we're going to choose that back face, and we're going to say this is fixed. Okay, so can't move anywhere. As you can see, there are other options, and there's advanced options down here as well. We're not going to look at those now. So open fixed, back to fixed, and click OK for that. Now we need some loads. So we've got a 250-pound load at the end here of our rectangular bar. So right mouse click, put on the force, and grab that end. And you see the default is normal. We don't want normal to that surface. We want it to come acting in the negative Y direction in SolidWorks or negative Z direction on the example. So I'm going to choose select a direction here, and I'm going to just choose that edge. And I want to reverse the direction, so it's acting downwards. And I need to change my units to IPS. Put in 250. Okay. All right, so now we've got our model loaded with a load here, and it's constrained by a fixture at this end of the circular rod. So the finite element part is to now discretize this geometry into finite elements. Okay, and you can read more about it in that textbook that I showed you before. All right, so if you right mouse click on there, create the mesh, and we'll just leave it as default for now. There are other things to look at. We'll do that in class. And we might slide this slider a bit later on just to show some things. So you can see now that the finite elements or the elements are shown. So this geometry is discretized into little pieces, and we can now use this to approximate the behavior of our complete shape. So the addition of all of these little elements approximates the behavior of the more complex overall shape. So now we've done that, we can click run this study. Right, and in seconds, right, we have some pretty colors that tell us something about what's going on in this model. Okay, so the default output here is von Mises. Currently, it's in newtons per meter squared. So we can change that. I'll show you that in a second. So firstly, right, you've got an output here. You need to understand what this means. Right? What is this von Mises stress that you're getting output? If all you do is put this in your report and say the von Mises stress is this, but you don't even know what that is, what on earth are you doing, right? So part of this week's class is to revise what you've done before and extend what you've done before, so you can make use of these tools in a more understanding and rigorous way, and actually know what you're doing rather than just clicking buttons and making pretty pictures appear. Okay, so at the moment this is von Mises. Let's edit this. So if you right click, you can edit the definition, and we can change that to PSI. Okay, let's do that. And now we've got PSI. If we go over to our model that we have, or the results that we have in the textbook, you can see we've got something different here. So firstly, the way the results are presented are different. And also the stress output is different. So they've chosen stress X. Right, so I'm going to show you how to do that. But in class, we're going to discuss why they've chosen stress X here. Right? So how do we do that? We can change this one if we like. So if you right click and go to edit definition, we can change that to all of these options. I'm going to start a new one, but the other thing that we might do is, so the chart options control what happened here and how this looks. Right? So we can show the max annotation, so that will highlight for you where the maximum stress is. In the textbook here, they've got different format for the stress output. So we can change that to floating. So now we've got the same, what's that, 8 significant figures. And if you know me from previous subjects, you know this is my pet hate, but I will leave it for now. All right, so, the other thing that we didn't do, so is here you can see the elements on the model. So let me go here and go to settings, and we can change that to mesh. Okay, so we can now see the elements on here. Right. If we want to keep the von Mises stress and have another stress plot with the stress in the X direction, like we have over here, we can just start a new one, stress in the normal direction, make it PSI, chart options. So the good thing with these later versions of SolidWorks is all of these 3 options are in the same dialog box. They didn't used to be, which was really painful. So we can click on that. And that's done now. Oops, I didn't change, I didn't change the those. Whoops, not general, floating. How we see those. All right, so we can see here we've got stress X 30-odd thousand PSI. Here in the textbook, we've got 30-odd thousand PSI. All right. What you can see here in the textbook results is that our finite elements are much smaller. All right, so let's go and change that in our model. So right click here. I can't remember if it's in settings or definition, doesn't really matter anymore. Whatever you do, you'll see the options to change. Oops, what have I done here? Yeah, so I want to recreate the mesh. Sorry about that little bit of a mistake. So yeah, I need to change the mesh. So I was thinking about results rather than the mesh. So tells you that remeshing will delete the results for the study. Yep, we know that. So click on that and we can adjust the mesh parameters here. But we're just going to keep it simple, stupid, and this is pretty stupid, but we're just going to slide the slider up here and just click on that. And we've changed the mesh, so you can see we've got much finer elements or much smaller elements. Run the study again. Takes a little bit longer. Too much longer. There we go. And we've now got some new results. Now, what do we see? We've now got a maximum stress of 40 or nearly 42,000 PSI and in a different spot. What's going on? Which is the right answer? The answer is neither of them are the right answer. They're both meaningless, fictitious results that you cannot or you should not use to do any further analysis or make decisions on what you do with your design based on these numbers. Okay. And we'll talk about that more in the tutorial. Okay, so here we got 42-odd thousand. We can change that again. Let's go to create mesh again. Yes, we know we're going to change our results, and we're going to slide it all back the other way and run it again. So you can see now much bigger elements, much coarser mesh. Run the study, and we get a different number again. Okay. And looks like a different location again. Right. So does this mean that all of our results here are meaningless or fictitious? No, it does not. But as engineers, using a tool like this, you need to know how to work out which are the good ones and which are the bad ones. Yep. All right, so I think that's about it for what I wanted to show you in this video. In class, we'll spend a lot more time interrogating this model and talking about these things and trying to compare the results that we get in our finite element analysis with the results that we get from our theoretical calculations, some of which you will have done previously in other subjects. Some of you may have done it and others won't have done it. So we're going to look at that in the tutorial. So I'm going to stop sharing my screen now. So that was probably a little bit longer. I haven't looked at how long that video was. It's a little bit longer than I wanted, but hopefully that was helpful for you and gets you up to speed for getting involved with the tutorial this week. All right, see you in the class then. Bye.